groups. A group G is a set together with a law of composition, which we denote by this dot, that satisfy certain properties. The first property is called the closure property, which means the following. If A and B are two elements of the set G, then the composition of A and B, which we denote as A dot B, is also an element of the set G. The second property that is satisfied by the composition operation is the following, and we call it the associativity property. If A, B, and C are three elements, any three elements of the group G, then we can construct the composition in two different ways. First, we can take the composition of B and C, that will be an element of the group because of the closure property. And then we take the composition of that element with A. So that is one way of taking the composition of these three elements. And the other one is the following. We can first take the composition of A and B and then take the composition of the result with C. And if these two gives the same element of the group, that is if A dot B dot C and A dot B dot C are the same for all elements A, B and C of the group, then we say that the composition operation is associative. And the third property that should be satisfied by the composition operation is the following. There should be an element which we denote by E and call the identity element, such that the composition of any element A of the group with this particular element E gives that element A back. So A composition E equal to A for all elements A of G. And the fourth property is the existence of an inverse for every element A of the group. That is, if we take any element A of G, then there exists an element which we denote by A inverse and call it as the inverse of A, such that the composition of A with A inverse is equal to the identity element of the group. Now these four properties, that is those given by equation 1.1 to 1.4, also imply the following. For each element A of the group, the inverse A inverse is unique and satisfy the following property. A composition A inverse is E, which was the same thing as equation 1.4, but these four properties together also implies that A inverse composition A is also the identity element E. And secondly, the identity element E is unique and satisfy A composition E is A, which is the same as equation 1.3. But these four properties together also implies that E composition A is also A. Now the group composition is sometimes called the group multiplication, and the group is sometimes specified as the pair G, dot, where G represents the set of elements of the group and dot represents the composition operation. If the number of elements in a group is finite, then it is called a finite group. Otherwise, it is called an infinite group. For a finite group, the number of elements in a group is called the order of the group. If the group is not finite, if it does not have finite number of elements, then it can be of two types. Infinite groups can be of two types: discrete or continuous. If the elements in an infinite group can be identified as the first element, second element, third element, and so on, then we call it a countable group. So countability means that there is a one-to-one correspondence between the group and the set of integers. So it is a discrete infinite group. If it is not a discrete group, then the group is called a continuous group, in which case there will not be a one-to-one correspondence between the set of elements and the group and the set of integers. The elements of a discrete infinite group can be labeled in the following way. We write it as Gi, where I is an integer. We now consider some examples of group. Let us first consider the pair, which is given by the set of two elements -1, 1, and the composition operation dot, and which in this case we take as real multiplication. This set is a set of two real numbers, -1 and 1. To verify that this is a group, we check whether it satisfies all the properties required of a group. First, we consider the closure property. The closure property means that the composition of any two elements of the group should also be an element of the group. So, we first consider the composition of the first element, which is -1 with itself. So, -1 times -1. By the way, this dot now represents the real multiplication. So, it is -1 times -1, which is 1. And as we see, 1 is an element of the set. Similarly, we consider the composition of the first and second elements, -1 times 1, which is -1, again that is an element of G, and then 1 times 1, which is 1, an element of the group. So closure property is satisfied. Next, we need to consider associative property, but we already know that real multiplication is associative, and therefore that is settled. The next one is the existence of an identity element. Here we see that the number 1 is identity under real multiplication, and therefore the identity element here is 1. If it is to be a group, then all elements should have unique inverses as well. First, we consider the element -1, and we see that -1 times -1 is 1, which means -1 is the inverse of -1. So we have -1 inverse is -1, and similarly 1 inverse is 1. So we see that the set of elements -1 and 1 together with real multiplication satisfy all the 4 properties required for a group. The number of elements in the set is 2, -1 and 1, and therefore G is a group, and it's a finite group, and its order is 2. Now we consider a second example. In this case, there are 4 elements in the set, They are complex numbers 1, I, minus 1 and minus I, and dot here represents complex multiplication. It can be easily verified that it is a finite group of order 4. That is because there are 4 elements. So the properties that need to be checked are first closure, and by considering the products of all elements among themselves, using complex multiplication, we can verify that the closure property is satisfied. And the second property that is to be satisfied by this set of elements and this operation is the associative property, and complex multiplication is associative, and therefore that is also satisfied. Now, under complex multiplication, this element 1 is the identity, because 1 times any other complex number is that complex number. We can also verify that every element has an inverse. For example, the inverse of this one, 1 is 1 itself. The inverse of I is minus I, and that is because I times minus I is 1. And inverse of minus 1 is minus 1, inverse of minus I is I. And therefore, it satisfies all the axioms that a group should satisfy, and it forms a group, a finite group of order 4. Now we consider a third example. In this case, we consider the set of integers together with the real addition as the group composition. So we need to check all the 4 properties. First of all, we see that the set of integers is closed under real addition. And that is because if we take any 2 integers, say n and m, and then add these 2 integers, we will get a third integer as a result. And therefore, the set of integers is closed under real addition. Now we also know that real addition is associative, and the identity under real addition is number 0. That is because any integer plus 0 is that integer itself. We also need to see that every integer has an inverse. To see that, we note that for any integer n, there exists another integer which we denote by minus n. For example, if n is equal to 2, we can consider minus 2 such that n plus minus n is equal to 0. Now 0 is the identity here, and therefore the inverse of an integer n under real addition is negative n. So we have also identified now that every integer has an inverse under addition. Now the number of elements in the set of integers is infinite, but it is countable, and therefore it is a discrete infinite group. So the set of integers under real addition is a discrete infinite group. We will now introduce another definition. If the group composition is such that for any 2 elements A and B of the group, if A composition B is equal to B composition A, then the composition is said to be commutative. So it's called commutative. And the group G will be called abelian. Now looking at this example, we can see that the group composition operation is real addition and real addition is commutative. And therefore, this group, the set of integers under real addition, is an abelian group. Now we consider a fourth example. Here the set we consider is the set of real numbers, and the group composition we are going to consider is real addition. Again, under real addition, two real numbers R and S gives another real number, and therefore we see that the set R is closed under real addition. Further, real addition is associative, and the identity under real addition is 0, which is a real number. And for any real number R, the inverse under addition is minus R. That's because R plus minus R is 0, the identity element. Therefore, we see that the set R together with real addition forms a group. The number of elements is infinite, and there is no one-to-one correspondence with the set of integers. Therefore, it is not countable, and therefore this is a continuous group. Again, the group composition operation is real addition, which is commutative, and therefore the group R comma plus, which is the real addition, is an abelian group. And we consider another example. In this case, we consider the set of all positive real numbers, which we denote as R plus, the set of all positive real numbers. So R plus is all elements are greater than 0. And as a group operation, we consider real multiplication. So we need to check whether it satisfies all the properties that should be satisfied by the group elements under the composition operation. For any two elements R and S of R plus, so since they are elements of R plus, R should be greater than 0 and S should also be greater than 0. So in that case, the product RS, that is the result of real multiplication of two positive real numbers R and S, will also be a positive real number, and therefore R composition S is also an element of R plus, the set of positive real numbers. So closure property is satisfied. Now real multiplication is associative, so associativity is also satisfied. Now under multiplication, the identity is the number 1, and that is because 1 times R, where R is a positive real number, is simply R. Therefore, the identity in this case is 1. Now we also need to check whether every element in the set has an inverse under real multiplication. For this, we note that an element in R plus is always greater than 0. If R is an element here, an element of R plus, it implies that R is greater than 0. Now we can also see that R times 1 by R is equal to 1, and 1 by R exists because R is greater than 0. It is not equal to 0. So 1 by R times R is 1, which is the identity under real multiplication. So we see that under real multiplication, the set of elements R plus satisfy all the properties required of a group. So again, it is a group, it's an infinite group, and it's a subset of the set of real numbers. It is a continuous group. The multiplication of real numbers is commutative, and therefore the group is abelian as well. Now we consider a more sophisticated example. We consider the set of non-singular square matrices of order n. Under the group multiplication, sorry, under the matrix multiplication. By non-singular matrix, we mean matrices that have non-zero determinant, so that the inverse of the matrix exists. Now we check whether it satisfies the properties required of a group one by one. So let A and B be two elements of the group. That means A is a square matrix of order n with determinant not equal to 0, and B is also a square matrix with non-zero determinant. Then since A and B are two n by n matrices, the matrix multiplication gives you the product A dot B as another n by n matrix. To satisfy the closure property, we also should show that A dot B, that is the resulting square matrix, should also be non-singular. For that, we have to show that the determinant of A dot B is non-zero. Now, from the properties of the determinants, we see that the determinant of the product of A and B is equal to determinant of A times determinant of B. Now, determinant of A is non-zero and determinant of B is non-zero, which means the product is also non-zero, which implies that A dot B has a non-zero determinant. Or in other words, A dot B is an n by n square matrix which is non-singular, and therefore the composition of A and B is also an element of the group. The closure property is satisfied. Now the matrix multiplication is associative, therefore associativity is also satisfied. And we also note that the identity matrix, the unit matrix of order n by n, is the identity for matrix multiplication of n by n square matrices. For any n by n square matrix, A times In is equal to A is equal to In times A. So there is an identity for the non-singular matrices under matrix multiplication as well. Now, every element of this group is non-singular. For example, if A is an element of the group, then determinant of A is not zero, which implies A inverse exists, and that satisfies A times A inverse is equal to the identity matrix or unit matrix of order n. This was the identity of the group composition. So that means the inverse matrix exists for every matrix in this set. So which implies that the set of non-singular square matrices of order n forms a group. So we consider one more example. The set of all matrices of order m by n. This is no longer a square matrix. It may be, but in general, m and n could be different. So the set of all matrices of order m by n under matrix addition. This can be easily verified to be a group. Matrix addition is of course associative. Now the sum of any two m by n matrices is an m by n matrix and therefore closure is satisfied. And as I have already said, associativity is also satisfied. The identity matrix under matrix addition is the null matrix of order m by n. And for any m by n matrix A, the matrix obtained by multiplying A with minus 1, which we denote as minus A, is the inverse, because A plus minus A is equal to the null matrix of order n by n. So we see that it satisfies all the properties required for a group. Now hereafter we use a simplified notation AB for the composition of two elements A and B of the group. Instead of writing A dot B, we will use AB. Now we consider the group of transformations. So let us first discuss what a symmetry transformation means. The transformations that leave a system invariant are called the symmetry transformations of the system. For example, consider a circle. Now consider an axis passing through the center of the circle and perpendicular to the plane of the circle. If we rotate the circle about the axis passing through the center and perpendicular to the plane, we will still get the same geometrical figure. So that means rotation under this axis does not change the geometry at all. So, considering the circle as the system, the transformation is rotation of the circle, rotation of the system about an axis passing through the center of the circle and perpendicular to its plane by any angle. So this is an example of a symmetry transformation. Another example would be a square and we can again consider an axis perpendicular to the plane of the square and passing through its geometric center. Now, rotation about this axis by an angle of pi by 2 will take this corner to this point, this corner to this point, and this corner to this point, and this corner to this point. And the result is again another square. But which is exactly same as this one. So there is no way of distinguishing between this figure and this figure. So rotation about this axis by an angle pi by 2 radians is the transformation here of the system of a square. And therefore, this rotation is a symmetry operation of the square. Now we demonstrate that symmetry operations or symmetry transformations form a group if we define the composition law for the group in the following way. Let A and B be two symmetry transformations. So which means the action of B or the transformation corresponding to B of the system leaves the system invariant. If it is a circle and B is rotation by some angle, say theta 1 about the axis I was mentioning earlier, a rotation about this axis by theta 1 is not going to change the geometrical structure of the figure, which will still be a circle. So rotation by theta 1, which is B, does not change the circle. And rotation by another angle theta 2, which we call as the transformation A, will also not change the circle. Now we can define the composition of these two operations A and B in the following way. We first consider the transformation B on the system, followed by the transformation A on the result of the action of B on the system. Now since B doesn't change the geometry of, for example, this circle, and so the action of B on the circle leaves or gives the circle itself the same figure, and the action of A on the result will also give the same figure, and therefore A dot B, which is how we define this composition, that is B followed by A, will also leave the system invariant, the circle, the geometry of the structure unchanged. So that means B followed by A is also a symmetry transformation. To generalize it, if A and B are any two symmetry transformations, and B acting on or B transformation on the system followed by A transformation on the result of B on the system will also leave the system invariant, and therefore is a symmetry transformation. And we define the composition of A and B as B followed by A. So we have already seen here that the composition AB, A dot B, is closed. That is because A dot B, the composition which we defined as B followed by A, is also a symmetry transformation. We can now check whether this composition satisfies the associativity property. For that, we first consider the following composition: B dot C and then composition with A. So according to our rule of composition of symmetry transformations, A dot B dot C is equivalent to B dot C transformation on the system followed by A. But B dot C is C transformation followed by B, and therefore this whole thing is C on A followed by B on its result followed by A on the result of C followed by B. So in shorthand, we could say that this is equivalent to C followed by B followed by A. Now we consider a second way of composing these three elements, these three transformations, that is A dot B dot C, which is equivalent to C on the system followed by A dot B. But A dot B is B followed by A. So this composition can now be understood as C followed by B followed by A, which is the same as this composition. So that means A dot B dot C is the same as A dot B dot C. That means the composition that we have defined here also is associative. The third one that we need to check is the existence of an identity transformation. We can always define a transformation which does nothing to the system. So that is called the identity transformation, which is a symmetry transformation because it does not change the system at all. So we see that there is an identity transformation as well. Now suppose there exists a symmetry transformation which takes the system from S to S dash, but both S and S dash states are the same. So this may be thought of as our initial form of the circle, and under the transformation, say call it as A, it goes to S dash, which is also the circle, and both are the same. So now we can always think of a transformation from which will take the state S dash to S, that is going backwards. Since S dash state is the same as S, the transformation A is a symmetry transformation. So S and S dash are the same state. That means the transformation from S dash to S is also not changing the state because S and S dash are the same. And if we denote this transformation by A inverse, we see that A inverse is also a transformation that does not change the system. And therefore, this transformation, the inverse transformation from S dash to S, is also a symmetry transformation. Now the composition of A and A inverse is actually the following. A inverse take S dash to S and A takes S to S dash. So that means the composition A inverse followed by A will take state S dash to S dash, which is nothing but the identity transformation. And therefore, we have identified this transformation A inverse as the inverse transformation corresponding to a symmetry transformation A. So we have first identified that there exists a transformation A inverse which will take S dash, which is obtained by the action of A on an initial state S, back to S. And then we see that since A is a symmetry transformation, S dash and S correspond to the same state, and therefore the transformation from S dash to S also is a transformation from the state to itself, and the transformation does not leaves the system invariant, and therefore A inverse is also a symmetry transformation. So there exists a transformation A inverse which is also a symmetry transformation. Further, the composition of A and A inverse is the identity transformation. And therefore, we see that for every symmetry transformation A, there exists a transformation A inverse, which will be the inverse transformation. Now we see that the set of all symmetry transformations under the group composition law we have described here forms a group. And the group of all symmetry transformations of the system is called the group of symmetry of the system, or the symmetry group of the system. Now we examine the symmetry group of a square in detail. The square is represented by this, and I have given labels A, B, C and D to the vertices, and these are not part of the square. They are simply given there so as to keep track of various transformations, the changes that happens to this figure under various transformations that we are going to consider. And we have also specified some indices for the locations with the purpose of identifying what happens under a particular symmetry transformation. First of all, as we have already mentioned, we see that if we consider an axis perpendicular to the plane of the square and passing through the geometric center, which is given by this red circle, the point that is at the geometric center of this square, then a rotation by pi by 2 about this particular axis will leave the square unchanged. To appreciate that, we first see this. This is the square with the vertices labeled as A, B, C and D. And we consider a rotation by pi by 2 about an axis passing through this point and perpendicular to the plane of the square. If you rotate it by pi by 2 radians about this axis, we see that this vertex A goes to this position and this vertex B goes to this position. And coming back to this figure, we can see that A under this rotation by pi by 2 about an axis perpendicular to the plane and passing through the geometric center will take this vertex labeled A2 from position 1 to position 2. And similarly, B will go from position 2 to position 3. And C to D and D to A. Symbolically, we can write it in the following way. A rotation by pi by 2 about this particular axis on a square with labels A, B, C and D will take the square to the following configuration, where this vertex A over here now goes to this position and this vertex label B goes to this position and this vertex label C goes to this position and vertex label D goes to this position. And remembering that these labels are not there in the square to begin with, and these were labels that we supplied for our own convenience, keeping track of these changes under this transformation, we see that this figure is exactly same as this figure. And if we erase these labels, and in fact these labels were not there initially. So we have an initial state given by this and a resultant state given by this, which we could have distinguished provided these labels were already there, but square did not have those labels, and therefore there is no way of distinguishing between this state and this state in the absence of these labels. So this rotation is a symmetry transformation. Now this is a rotation by pi by 2, which we may write as 2 pi by 4. Now the axis is perpendicular to the plane of the figure and is passing through this geometric center, and a rotation by 2 pi by 4 is a symmetry transformation, and such a transformation is denoted as C4. In general, if we have an axis and a rotation by 2 pi by n about that axis leaves the system invariant, we will call that axis as a Cn axis, and the group operation is also called the Cn operation. In this case, the rotation is by pi by 2, and therefore it's 2 pi by 4, and we call this operation a C4 operation. So we now see that a rotation about this axis, about the C4 axis by pi by 2 is a symmetry transformation. So the state, the square remains unchanged under this transformation. And again, if we add one more rotation, one more pi by 4 rotation, that will result in a rotation by, a total rotation by pi radians about the same axis. And that is also a symmetry transformation, because in that case also the square will be mapped to the square itself. And we can do one more rotation, which is a C4 followed by a C4 followed by another C4, which is equal to a rotation about this axis by a 3 pi by 2 radians. So to see that, we consider that C4 2 times acting on the square is like this. It's a rotation by 2 pi by 2, so rotation by pi by 2. So this vertex label A goes to this position, and this vertex label B goes to this position, and this vertex goes to this position, and this vertex goes to this position. So we have A goes to C, so that is A here, and B here, B goes to this position, C and D. So this is a rotation by pi radians, and this is also symmetry transformations. And if you rotate by 3 pi by 2 radians, this is equivalent to a pi by 2 rotation followed by pi by 2 rotation followed by a pi by 2 rotation. So that will take this A to this position, and this vertex to this position, and so on. And the result would be A coming here, A, followed by B here, C and D. So this is also the same geometric figure. In the absence of these labels, it's a symmetry transformation. So we can now consider 4 pi by 2 rotations about this axis, one by one. So the first one will take it to this, the second one will take it to this, third one, that is this, and the fourth one take it all the way back to this. Similarly, B comes back to its position, C to its position, and D to its position. So the result of this, even with the labels, is the same figure with the same set of labels. So that means a rotation by 2 pi radians, which is 4 pi by 2 rotations about the same axis, the C4 axis, leaves the system completely unchanged. So it does nothing to the system. So this is the identity operation. Now writing a C4 rotation followed by another C4 rotation as C4 composition C4 which we call as C4 square, and we also know that this is a rotation of pi radians about the symmetry C4 symmetry axis. We using the same notation we can write so this is rotation by pi radian. Then a rotation by 3 pi by 2 radian about the C4 axis is C4 C4 which we denote as C4 cube, and a rotation by 2 pi radians will be denoted as C4 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 C4. There's a pi by 2 rotation, pi by 2 rotation, pi by 2 rotation, and pi by 2 rotation. So together it becomes a 2 pi by 2 pi radian rotation, which we denote as C4 to the power 4. But we have already seen that C4 to the power 4, which is rotation by 2 pi radian, is also the identity under this composition. It is the identity transformation. Now this generalizes. If we have a Cn axis, that means a rotation about a symmetry axis by an angle of 2 pi by n radians, we can construct Cn square, Cn cube, etc. But then Cn to the power n is a rotation by 2 pi by n into n. So 2 pi by n into n, which is 2 pi radian, which does nothing to the system, and therefore is the identity. So if we have a Cn axis, associated with it will be n rotations, which we denote as Cn square, so on up to Cn to the power n, which is equal to the identity. So that is the generalization of symmetry under Cn axis. So we have now identified 4 symmetry operations, symmetry transformations of the square. They are C4 square, C4 cube, and C4 to the power 4, which is the identity. Now there are 4 more symmetry operations for the square, which can be seen by first considering this axis that we have labeled 5, 7. So we can consider this line labeled 5, 7, and we can consider a plane that is perpendicular to the plane of the square and is intersecting it through the line 5, 7. Then we can consider a reflection of the square about that plane. Now, since calling this 5, 7 line as the x-axis, we may call it as this particular reflection operation as, say, mx, and under this reflection, this point B, the vertex B, will go to vertex C, and vertex A will go to vertex D, and vertex D will go to vertex A, and similarly vertex C will go to vertex D. So mx is the reflection about a plane represented by this line, which is the intersection of that plane with the plane of the square. Now under this reflection, D goes to A goes to D, C goes to B, and B goes to C. So the result is DC and AB. Now we can also consider reflection about the plane represented by this line. So under this reflection, A goes to B and B goes to A, and D goes to C and C goes to D. And that is what we got here. So B and C go to this line and A and D go to that line. Now we consider a plane that intersects the plane of the square through the line AC, and we consider reflection about this plane. So here under this reflection, A and C remain unchanged, but B and D gets interchanged. So the result is A and C remain unchanged and B and D remains interchanged. And we call this operation as sigma u. By the way, the earlier operation, reflection about a plane represented by this line, is called my. And next we consider a plane represented by this line. The intersection of the plane with the square gives a line BD, and we consider the reflection about this plane. And again we see that B and D does not change under this reflection, but A and C get interchanged. And the operation is denoted by sigma V. So C and A interchanges, but B and D remain unchanged. And that exerts the set of symmetry transformations of the square. And enumerating them, we have C4, C4 square, C4 cube, C4 to the power 4, which is the identity, then mx, my, and sigma u, and sigma v. Now we can consider the composition of these operations, and we should verify that it is closed. The composition is already associative because they are symmetry transformations, and we have generally shown that the symmetry transformations are associative. And we have also shown that every symmetry transformation has an inverse as well. We just need to identify the inverse elements out of these set of elements. First of all, we note that C4, C4 square, C4 cube, and C4 to the power 4 are closed under a group composition. That is, C4 times C4 square is C4 cube, and C4 square times C4 to the power 3 is which can be written as C4 square times C4 composition C4 to the power 2, but this is C4 to the C4 square times C4, but this composition is C4 to the power 4, which is identity. So the result would be identity times C4, which is nothing but C4. And similarly, we can verify that these four elements are closed under group multiplication. Now we have also, we can also verify that mx square is the identity. To see that, we note the following. So mx transformation on the square is, they label them as A, B, C, and D, and it is a reflection about this plane. So the result is A and D gets interchanged. So D, then C and B gets interchanged. So DC AB. Now mx square acting on, so what will be mx square acting on ABC? So mx square acting on ABC is nothing but ABCD is mx composition mx ABCD, but that is equal to mx acting on ABCD is given by this. So DCAB. So again, it is reflection about this plane which interchanges A and D and B and C. So AB goes back and we get ABCD, which is the same as this. So mx square does nothing to the square. So it is the identity transformation. Similarly, we can show that my square is also the identity transformation, and so are sigma u square and sigma v square. We can also consider the composition of one of these rotations with any of these reflections and show that they also result in one of the elements given here in this set. A convenient way of representing all these compositions is in terms of what is called the group multiplication table, in which we arrange the products in a tabular form. In this table, we have a header row and a header column, and the row headers correspond to the elements of the group, and so are the column header. So are the column headers. So in this particular case, and now the symmetry operations, the symmetry transformations of the square form a group called C4B, and so that is the label for this group. So that is put here, and the row indices correspond to the elements of this set C4. So the elements are E, C4, C4 square, C4 cube, mx, my, sigma u, and sigma v. Now the row headers are also the elements of the group. So E, C4, C4 square, C4 cube, mx, my, sigma u, and sigma v. Now considering a particular cell in the table, the element of the group placed in that particular cell is the result of the composition of the element given in the column header followed by the element given by the row header. So here this element C4 is equal to C4 square, that is the column header, composition with C4 cube. Now for any element in this group multiplication table, the same rule follows. So for example, if we consider this particular element, this will be the product of mx times sigma u, because the column header is sigma u and the row header is mx. So the column header is the first transformation and the row header is the second transformation following the column header. So this is equal to mx times sigma u, and we can find the product, and that will be, the result will be written in that particular cell. So this is equal to C4Q. The details of finding all the elements of, so all the results of the compositions is given in exercise 1 and it is provided along with the notes. Now if you look carefully, the row headers are not given in the same order as the column headers. We could have written in the same order as the column headers, but this is done so that the diagonal entries in the table are all the identity. For that, the requirement is that for the, say, the ith column or the nth column, and we have the nth element of the group, and then the corresponding row header should be such that the product of the row header with the corresponding column header. So if it is the nth column, then the nth row header is such that the product of that row header with that nth column header will be the identity element. So that means if we consider the nth column, then the header of the nth row should be the inverse of the header of the nth column, so that their product will be the identity element. And this way of writing group multiplication will be helpful when we later learn the regular representation of groups. Now looking at the group multiplication table, we can easily see that every element over here has an inverse element, and that's why we have an identity element in one of the cells in every row or in every column. By looking at the group multiplication table for C4, we also see that the product of any two elements in the set is also one of the elements of the set. So closure property is satisfied. Then associativity is already satisfied because of the way in which we compose the symmetry transformations. The identity, existence of the identity is also established, and now we have established that every element has an inverse aspect. Looking over here, C4 has an inverse given by C4 cube, C4 square has an inverse C4 square, C4 cube has inverse C4, Mx has inverse Mx, My has inverse My, sigma u has sigma u as its inverse, and sigma v similarly has sigma v as its inverse. So that means these 8 elements, 8 transformations forms the symmetry group of the square.